Hey folks, it's Mr. Moray, and I'm coming to you today with a little video for Course 2 Honors, reviewing what we have talked about with regard to factoring. So in this video, what I'm going to do is I'm going to kind of give you a little refresher on all of the factoring skills that we've actually talked about, if you think about it, over the past couple of years as we prepare to close things out with rational functions. This is going to be a really important skill because we're going to need to break those down, and sometimes it has to do with factoring. Okay, so I thought I would start by kind of breaking down the kind of mindset that we want to go through when we're looking at any kind of polynomial. Okay, so the first thing we always want to do is we always want to see, is there a GCF that I can factor out? That is there something that I can see in every single term of the polynomial that can first be removed to make the polynomial simpler? If I ever ask you to factor completely, it is important that you take out a GCF. Once you've determined whether to take out a GCF, the next thing you'd want to see is the remaining polynomial quadratic? Because if it's quadratic, then we can just use the skills that we've learned in Course 1 Honors to finish it out from there. And so in Course 1 Honors, we learned about how to factor special cases, and then we talked about how to factor using the box, or what we might call unfoiling or undistributing, okay? And that kind of took us through Course 1. And so this yellow dotted line represents the borderline between Course 1, which is above, and the new skills we learned this year in Course 2, which are below. So this year what we learned is we can take it further. If it's not quadratic, well, we can see if it's cubic. And if it's cubic, we have some new ways to factor. If it's a sum or difference of cubes, we can use our rule, same, opposite, always positive. Okay, and that should not be actually b cubed. This should be b squared. Okay. Or if not, we can see if we can use the skill of factoring by grouping. Something that also works on quadratics, but which I don't tend to use as much. And if none of those strategies work, our final strategy would be to see if we can use the rational roots theorem by finding essentially factors of the constant term and plugging those in to see which one makes the polynomial 0 and going from there. Okay, so again, the idea is there's many skills that we've learned over the past couple years to break them down. We've learned these skills above the yellow line in Course 1 Honors, and then the skills below the yellow line we really focused on in Course 2 Honors. So the first skill I'm going to talk about is the greatest common factor. So what I talked about in the beginning of the year when we first started to really delve into factoring is that when you are working with any polynomial, the first thing you always do is look to see whether there's a greatest common factor, because that will always make the process of factoring simpler. And if you do factor, you are required to remove the greatest common factor anyway. So since you have to do it anyway, you might as well just do it first. So for example, in 3x squared plus 9, the greatest common factor is 3, right? There's a 3 in the first term and a 3 in the second term. So I write this as 3, and then what's left is x squared plus 3. And then what's inside will not break down any further because this does not have any real zeros, right? There's no real numbers that make this equal to 0, and so I am done. On the second one, as you can see, you can sometimes have not only a number in common, but also a letter in common, right? And hopefully this is starting to kind of come back to you guys. So 4x, and I have x squared, because 4x times x squared is 4x cubed, plus 3x, because 3x times 4x is 12x squared, minus 4, because negative 4 times 4x is negative 16x. Okay, and then where you'd go from there is what we'll see is you can actually break this down even more. And so what we'll see is, right, you always have to think about how can I break things down more. Okay, and so this is actually x plus 4 x minus 1. Okay? So you always have to look for ways to break things down. But the main idea is the fact that you can remove a greatest common factor. The fact that this is completely factored and the fact that this is the answer is not necessarily obvious just from looking here. The other thing we might remember is that you can actually factor out multiple letters. So here, all terms have a 2 in common, they have one x in common, and they have one y in common. And if I remove these, what I have left is 3 to get the 6, y, because if I multiply 3y times 2xy, I get 6x y squared. And now here I'm going to do minus, because it's a negative, 1x. Because here if I multiply, I get 2 times 1 is 2. X times x is x squared. And then we have the y. So it's 3y minus x. And I cannot break that down any further. And finally, we could even use 3 letters. So the greatest common factor here is 3. Each of them have an x squared in them. Each of them have the biggest power of y that they all have in common is y cubed. And then they all have a z in them. So here we have 3 times negative 4 is negative 12. There's no more x's because we already have our x squared. Y to the third times y to the fifth equals y to the eighth. And z times z squared equals z cubed. All right, now 3 times 2 is equal to 6. X squared times x is equal to x cubed. Y cubed times y squared is equal to y to the fifth. And z times z is equal to z squared. Finally, on the last one, it's going to be 1. 1 times 3 is 3. 1 times x squared, we're already good there. Y cubed, we're already good there. And z, we are actually also good there. So that one's actually just plus 1. So hopefully this made sense to you in terms of our first step with regard to factoring out the GCF. Please rewind and refresh if there's anything that was difficult or didn't make sense. And then when you're ready, I'll move on to the next case. Okay, so case 2 was the case that we spent a lot of time talking about last year and then kind of opened up this year, refreshing, so to speak. And that is quadratics. So once you've removed the GCF, the next thing you should try to see if you can do is break down a quadratic. Okay, and because a quadratic, if we can break it down, we already have the skills to do it. So one thing you're noticing about this flowchart is the idea is to go lowest energy to highest energy. It is, I would assert, easier to factor out a greatest common factor in most cases, at least that we'll see, than it is to factor using a quadratic. So here, it depends on the scenario. So here, remember, we talked about a couple ways to do it. So the first thing we're going to do is we're going to look to see if it's a difference of squares or a perfect square. And these formulas tell you what that looks like. So the first one is not. I know it's not a perfect square because 78 is not a perfect square. And also, I know it's not a difference of squares because a difference of squares, as you can see here, as this suggests, would not have a b value. It would be a square minus a square. There's nothing in between. See, there's 2 things here. There's 3 things there. So I'm going to have to go to unfoiling, or what I call using the box in reverse. So remember, we're building our box, and we're imagining that we multiplied 2 things together, and what we got was n squared minus 19n plus 78. Now, how could we have gotten that? Well, we know that n squared, that part will always be in the top left, and 78 will always be in the bottom right. Now I need to ask, how could I multiply 2 numbers and get 78? So I could have 1 and 78. I could have 2 and 39. I could have 3 and 26. Okay, 4 will not work. 5 will not work. 6 is going to have to work because 3 and 2 work. I'll just move that away so we don't get confused there. Okay, 6 times what is 78? 13. And I think I've got my answer. So notice that -6 and -13, when I plug them in, I get -13 times n for -13n, and then -6 times n for -6n. So I get n squared minus 19n plus 78. And so I would factor this as n minus 13, n minus 6. Okay, that's our standard factoring. Now, once we learned how to factor last year, the next thing we learned how to do is we learned how to work with scenarios where a was more than 1. And that included special cases. So here, a is more than 1. It's equal to 25. And so what we're going to do is we're going to do the same strategy. It's not going to be a difference of squares. But as you approach this, observe that this is a perfect square and this is a perfect square. So I know my 25g squared goes here and my 81 goes down there. So 25g squared, well, this is 5g squared, and 81, well, that's 9 squared. So let's try 5g and 5g, and since this is a positive, 9 and 9. When I do that, 9 times 5, that's 45. And when I take the 45g and the 45g, I get 90g. So perfect. So it's 5g plus 9 times 5g plus 9, which we need to write as 5g plus 9 in parentheses squared. Okay, now we have two things here, and that should give us a clue that in fact this is a difference of squares. So the difference of squares formula, as you can see here, tells us that we want to use 4j minus 3 times 4j plus 3. If you want to use the box, right, we've got 16j and we've got minus 9, but look, there's no b, which means these have to add up to 0, or in other words, cancel each other out. So if we assume that this is 4j and this is 4j to get 16j squared, sorry there, well, I need numbers that are going to cancel each other out. So the only kind of numbers that cancel each other out are opposites, and the only way that'll actually work is if the number in front of the j's are the same. Because, for example, if this was 16 and this was 1, then one of them would be getting multiplied, one of these, like the -3 would be getting multiplied by 16, and the +3 would be getting multiplied by 1. And then we wouldn't be canceling out. But here, what happens is we get 12j, and you get -12j, and they cancel for 16j squared minus 9. So that also backs up our answer. Finally, I thought I'd throw in this example here. And this example is getting at the fact and thinking about summarizing what we've done so far. So here, there's two things that are going on. Okay? The first thing that we've got going on here is that there's a GCF. Okay? So I noticed that 4 goes into every single one of these things. I noticed that 3 goes into them. 2 goes into them. And in fact, so does 6. So this has a GCF. So first, we remove the GCF. We get 4n squared plus 20n plus 6 goes into 15 twice. So something like that. And I actually know that 6/4 is $1.50. So that works. Okay? So first you take out the GCF, and now look how much easier you've made it for yourself. Okay? Now, if you don't take out the GCF, I'll show you what that looks like in a second. So what I'm going to do is I'm now going to factor the inside, and that will factor as 2n and 2n to get the 4n squared, and then 5 and 5, so that I not only get 25, but then I get 10n and 10n for a total of 20n. So this becomes 6, 2n plus 5, in parentheses squared. Now the other way to do it is we could have definitely boxed it from the beginning. And so basically I take a look at this, and this is not easy to be able to figure this out. That's the issue. So what I'm going to do is I happen to notice that, well, look, I need 24n squared and I need 150. So what I'm going to do is I'm going to do 30 and I'm going to do 5. And then what I'm going to do is I'm going to do 12 and I'm going to do 2. And this becomes 60n and this becomes 60n for a total of 120n. And then you've got 24n squared and 150. But here's the problem. When you do this, you get 2n plus 5 times 12n plus 30. And how I did this is in my head, I just distributed the 6 into one of these things. But you can see that the 12n and the 30 have a 6 in common. So when I ask you to factor completely, that means that you need to go into any factors and remove any GCFs. So you would have to go back into the 12n plus 30, that is, and remove that 6. And then that would mean once you see this, you've got to go back to the 2n plus 5 squared. So you see you get a same answer either way, but the thing is, if you don't pull out the GCF first, you still are going to have to take it out eventually. But think about how much harder it is to factor this in the box than this in these parentheses. So hopefully this made sense to you. If not, please take a moment and rewind. And then in a moment, I will move on to the next possible scenario. Okay, so the next thing we did, and this was an intro this year, is grouping. So this year we took a foray into grouping and cubics. And what we learned is that once we get into cubics, there's none of that quadratic formula to help us out, right? We can't just like simply put it together with like a factoring and like a box like we did last time. It just wasn't that easy. So what we learned to do is we learned how to factor by grouping, or we also learned the special case of sum and difference of cubes. And remember, our acronym here was SOAP. Same, opposite, always positive. That is, if you have a cubed plus b cubed, and I'll just go ahead and remember to make those squares, same sign, opposite sign, always positive. Okay? So when we group, remember, it comes back to the GCF. So we basically are going to break it into two little groups here. And so if you look at just these two terms in a vacuum, you're going to notice they both have an 8 in them, and they both have an r squared. And if I factor out that GCF, well, 8r squared times r equals 8r cubed. And then minus 8, right? If I do the 8r squared times minus 8, I get negative 64 r squared. Now, r and 8 only have a 1 in common. And so then remember what we do. There's one r minus 8 in common. So we remove the r minus 8 because each one of them has an r minus 8. And then when you remove it, what's left? 8r squared plus 1. And that's it, because there's no way we can break this down anymore. Okay, that's a little recap on factoring by grouping. Remember, you group them up, you look for the GCF, you group them so that when that GCF is removed, the things in parentheses are exactly the same. Then you factor out that thing in parentheses, and you write whatever those two pieces that are remaining are. So in this case, 8r squared plus 1. The second one is a difference of cubes, rather a sum of cubes. And remember, I never asked you to memorize this. So what we do is we first figure out the a and the b. So the a is u, and the b is 2, because u cubed is u cubed, and 2 cubed is 8. So what I would write this as is same. Well, actually, we want to use u. So same, opposite, always positive. And if we were to distribute this, we would get u cubed minus 2u squared plus 4u plus 2u squared, so you can see the u squareds are going to cancel out, minus 4u, so those u's cancel out, plus 8. So that cancels out the u squareds and the u's and just leaves an 8. So that's a sum of cubes. Third one, again, you can see these four things. We're going to try to do factoring by grouping. Okay, so what I'm going to do is I notice, okay, the greatest common factor of these first two terms, I'm just going to do this one in blue. The greatest common factor of these first two terms, this first group, they both have a 21 and they both have a k squared. And when I factor that out, I get k minus 4. And in the second piece, they have a GCF of 15. So I remove the 15 and I get k minus 4. So I now remove the k minus 4. I factor that out. And then what remains is 21k squared plus 15. Okay, and then 21k squared and 15 you can see as a greatest common factor. So I could have taken that out in the beginning. I could have seen, wait a minute, these all have a 3 in them, or I could have noticed it now. That's okay. So I take the 3 out. I always move the 3 in front. So I take 3 out of 21, I get 7. I take 3 out of 15, and I get 5. So remember, all GCFs need to be removed. This would not earn you full credit because the GCF is not removed. Okay, finally, this is a difference of cubes here. So this would be, okay, remember using the SOAP. So the A is, and I'll do this one. How about we do this one in green? So we have the A is equal to X, and the B is equal to 6. Why? Because 6 cubed is 216. Wait a minute, is it? Yes, 6 cubed is 216. And y cubed is y cubed. So I get same. Okay, now, here's where it gets tough. Opposite. Remember, we now need to do 2ab. So 2 times x times 6y. So that's 12xy. Because remember, you're multiplying by 2 here. And then always positive. Okay? All right. So please make sure you understood what I did here. This was essentially just breaking down factoring in which we're working with cubics. And this is talking about grouping and difference in sum of cubes. And then when you're ready, I'll move on to the final case. All right, so let's say we're at the point where GCFs are all taken care of. It's not a quadratic, so the quadratic factoring strategies are not going to work. It's not a cubic, so the cubic factoring strategies, right, the difference of cubes won't work because it's not cubic. We now have to ask ourselves, where do we go from here? Can we group it? Because if so, we can still pull off factoring by grouping when the biggest power of x is more than 3. In this case, for example, when we have a quartic, biggest power of x4, or a quintic, biggest power of x5. But otherwise, we are going to have to use the rational roots theorem. And I'll talk about that in a minute. Now remember, as part of the rational roots theorem, you are going to have it breaking down. So it would be like maybe x to the fourth, x to the squared, x to the third, x squared, whatever. Remember that some of the strategies higher up in our flowchart are strategies that you can revisit as the as the polynomial breaks down. Okay, but in general, when we're just looking at a polynomial as we are here, we're going to follow our flowchart. Okay, so here there's no GCF that we can take out. It's not quadratic, so none of the quadratic factoring strategies are not going to work. We can't use difference of squares. We can't use perfect squares. We cannot use the box and simply unfoiling. That will not work. Okay, similarly, we cannot use difference of cubes and sum of cubes because these are not cubes. And we also cannot necessarily, well, we have to see now, can we group them? Because none of the cubic stuff is going to work. So we take a look, and as it turns out, let's see. So I've got these first two terms, and they've got an x cubed in common. And by the way, I know I did have one in the last one. I decided to kind of move on from that. So I've got x cubed on the first one, and when I take that out, I get x minus 5. And here I've got a 2 in common, and when I take that out, notice I get x minus 5. So now I come in, I get x cubed plus 2 times x minus 5. Remember, if you remember back to earlier in the year, what I do from here, once I write out my factors, is I go through one by one and see if any of the strategies higher up in the chart is going to work. So first, x cubed plus 2. Is there a GCF? No. Is it a quadratic? No. So none of those strategies are going to work. Is it a cubic? Yes. Is it groupable? No. We can't group it up any more than it is. Is it a sum or difference of cubes? No, because 2 is not a cube. So therefore, x cubed plus 2 cannot break down anymore. And x minus 5, because it's linear, cannot break down anymore. And so we are, at this point, completely factored. And I'm going to undo that. There we go. All right. Second one, this one's quintic, but it's the same idea. All right, let's see what we got. So here, the biggest power of x is 3, so I'll take that out. And now I get x squared plus 6. And then over here, I see I've got a minus 2 in both of them. Because remember, when you do factoring by grouping, you want to make sure, okay, you always want to make sure that whatever you get in this parenthesis is the same as what you get in this parenthesis. So if I take out a negative 2, this is an x squared because negative 2 times x squared is negative 2x squared. And this is a plus 6 because negative 2 times positive 6 is negative 12. Okay? Now remember, you got the x squared plus 6's. We pull those in front. And I've got the x cubed minus 2. This cannot break down anymore. And I know that because it has no real zeros. Right? If I was to set x squared plus 6 equal to 0, there are no real numbers that make that true. And x cubed minus 2 is done because, again, it's almost the same as x cubed plus 2, right? This wasn't a difference of squares. It couldn't break down, etc. Or difference of cubes or sum of cubes. This is the same thing. It's not a difference of cubes. It's not a sum of cubes. It can't break down anymore. So we are done at this phase right here. All right, this one's going to be similar, so I'm going to come down to this one. And this one is one in which we have no way in heck that we are going to be able to break this down. In that, let's take a look. First, does it have a GCF? No, there's no GCF here. Second, is it quadratic? No, it's quartic. So the quadratic strategies won't work. It's not cubic either, right? I just said it was quartic, so the cubic strategies won't necessarily work. And since we can't group it, we're going to use the rational root theorem. So remember, the rational root theorem starts by saying, what are the factors of 8? Well, 8 could be plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. Okay, and then remember what we do is we then build our synthetic division table. So I put my 1, I put my negative 2, actually I put my 0, put my negative 2, I put my negative 8, so that's the x to the fourth, x cubed, x squared, and I actually need another 0 for my x to the first. Okay, and now I'm going to choose numbers and plug them in and see if it makes it equal to 0. I'm going to try first plugging in 1. So 1 comes down, 1 times 1 is 1, plus 0 is 1. 1 times 1 is 1, plus negative 2 is negative 1. Negative 1 times 1 is negative 1, plus 0 is negative 1. Negative 1 times 1 is negative 1, plus negative 8 is negative 9. So 1 doesn't work. I'm going to assume negative 9 probably won't work either. Let's try 2. So I bring the 1 down. 1 times 2 is 2, plus 0 is 2. 2 times 2 is 4. 4 minus 2 is 2. Okay, 2 times 2 is 4. 4 plus 0 is 4. 4 times 2 is 8. 8 plus 8 is 8 minus 8 rather is 0. Okay, so what that means is that x minus 2 is one of the factors because 2 makes the y equal to 0. And then what remains, remember we're doing synthetic division here. So x cubed plus 2x squared plus 2x plus 4. Now I repeat the rational root theorem again. So now I look at factors of 4. So 4, that's plus or minus 1, plus or minus 2, and plus or minus 4. So I rewrite. I've got my 1, my 2, my 2, my 4. And I'm going to start with, well, I'm probably not going to do 2. Let's try negative 2. So I bring down my 1. I get 1. 1 times negative 2 is negative 2, plus 2 is 0. Negative 2 times 0 is 0, plus 2 is 2. Negative 2 times 2 is negative 4, plus 4 is 0. So now it breaks down again. I've got x minus 2. And then because this is minus 2, the second factor is x plus 2. And then what's left is x squared plus 0x plus 2. All right, and basically at this point, there's really not much I can do to break things down any further. I can't factor the third thing, so I kind of have to leave it as is. But that is more or less the idea, folks, behind how you do the rational root theorem. So again, you start with the factors of the constant. You plug in until you find a 0. You use that to take a factor out, and then you use division to figure out what remains. By setting up this synthetic division table, as we talked about, it makes that process easier. So please make sure at this point, I've been going for a good amount of time, that you understand what I've done here. And then in a moment, I am going to move on to some problems for you to try. Okay, folks, so I've spent a good amount of time talking at you up to this point. So it's time for you to try. So what I've done is I've kind of given you a smorgasbord of different problems here, and these span the various cases that I've discussed in this video, from GCFs to quadratics to cubics to beyond. What I want you to do is I want you to take a minute. I want you to pause the video. I want you to try to factor these in order from easiest to most difficult, and then when you're ready, I want you to unpause and you can see what I got. Okay, so the first one is basically just a GCF kind of problem. So here, the biggest number that can go into the coefficients is 2. And then I'm not quite ready to drop that parenthesis because each of them has an x. This has an x and this has an x, and each of them has a y. So the 2xy comes out, and then what's left is 3x minus 2y squared, because when you multiply here, you get 6x squared y, and here you get 4x y cubed. And because it's a negative, you get the minus there. All right, second one, no GCF that I can see other than 1. We have the x squared minus 4x minus 21. So let's go ahead and box this one out. So I get x squared minus 21. So I get x and x. And let's try negative 7 and positive 3. So I get 3x minus 7x. And so negative 7 plus 3, that would be negative 4. So I get x plus 3 times x minus 7. Great. All right, this one, let's take a look. Is there any GCF, 3, 17, and 10? Other than 1, no. No variable in common. So I will go ahead and set up my box. So here we'll have 3x squared, and here we'll have positive 10. Just going to erase that. Now, I need to get 3x squared. So what would I have to multiply to get 3x squared? Well, this would be 3x and x. What about to get 10? Well, I got to be careful here. So I'm going to put -5 here and -2 here. And that's because a negative times a negative will give me the positive, but then a negative plus a negative will give me a negative. So I end up with 3x minus 2 and x minus 5. Hopefully it's coming back to us. It hasn't yet. All right, this one's going to be a difference of squares, and that's x minus 9 times x plus 9. So I'll just do that one. This next one's a little bit of a combination. So here they both have a 2 in common, right? So let's take out a GCF first. So I've got 4x squared minus 25. And the advantage of doing that is that I can now see that I've got a difference of squares. So I put in my 2. I do 2x minus 5. And I do 2x plus 5. All right. So now I'm going to go ahead. I'll just drag these down. And now I'm going to take a look. And this one is cubic. So again, GCF, no. Is it a quadratic? No. So difference of squares won't work. Perfect square won't work. Boxing is not going to work. So it is cubic. I can tell that because it's got a 3. So I'm going to try to do grouping. So I look at my first two terms. They have an x squared in common. I take out the x squared. I have x plus 1. Here, I have a negative 16 in common. X plus 1. Okay, so now what I'm going to get is I'm going to take out the x plus 1 and do the x squared minus 16. And I am done. Yes, right, folks? No, not quite. And that is because don't forget that you have to go back and look at each piece. So here, just like here, right? After I factored out, I then had to work the difference of squares. Here, I do the factoring and then I look at each piece one at a time. Can the x plus 1 be factored? No. Can the x squared minus 16? Yes, because it's the difference of squares. So this is x plus 1, x minus 4, x plus 4. Okay, so again, we're taking out a GCF. We're looking to get these things in parentheses to be the same. We're factoring that thing out, and then we're trying to look at whatever remains and just keep going until everything is broken down as much as possible. Remember, anything linear, anything of the form, any factor of the form mx plus b cannot be broken down any further than it already is. So the goal is, if you see all of them kind of like that, then you're in good shape. All right, moving on down, I now have this one, which is a challenge. Now here, let's take a look. So let's say I take a look at these first two terms. Okay, they have a 30 in common and they have a u in common. So if I factor out the 30u, I get v plus 1. But there's no way I'm going to get a v plus 1 here, right? So I need to vary up my strategy. How could I do that? Well, maybe there's a way I could do it. And what you actually need to do here is you need to rearrange the term. See how I know? See, I can see that this has a v and this has a v. So I'm going to use the commutative property, which says that it doesn't matter the order that you add numbers or expressions. And I'm going to rewrite this by moving the 25 and grouping it with the 30. And then I'm similarly going to put the u squared in front, and I'm going to group the 30u together like this. And again, because of the commutative and associative properties, it doesn't matter how you group up numbers, and it doesn't matter the order that you have numbers when you are doing things like addition. Okay, that the fact that there's a commutative property means that it doesn't matter. If the commutative property didn't exist, we could not assume that we're able to do this. So now I'm going to factor out, let's see the GCF. So these both have a 5 in them. and they both have a v in them. So this would be 6u plus 5. And here, these both have a 6 in them, and they both have a u in them. And this would be 6u plus 5. So we have 5v plus 6u times 6u plus 5. Okay, because this one has the 5v and this one has the 6u. And you can see that I know I'm successful here because I've got the 6u plus 5 coming up in both. Okay, remember the order of the factors in general does not matter because, as I noted, right, just like with addition, multiplication, the order does not matter. So, for example, if this one up here was x minus 4, x plus 1, x plus 4, that's fine. Just as if this one was 6u plus 5, 5v plus 6u, that would also be perfectly fine. All right, last one, super duper challenge. So this one is going to be factoring by grouping is where I'm going to start. So let's, again, break it down. It doesn't have a GCF numerically or with regard to your letters. They don't all have at least an x in them, so I can't factor out an x, and there's no number that's shared among all of them. The last three terms do have a 2 in them, but the first term does not, the leading term, so I can't factor out a 2. So the GCF is out of the question. Then I go to quadratics. It's not quadratic, so the quadratic strategies will not work. Now I go to cubics. It's not cubic, so the difference of cubes and sum of cubes is obviously not going to work. Now I try to see if grouping is a possibility. If I can group, right, then I'm in a scenario where that would be something I would do. Otherwise, I would do the rational roots theorem. I want to try to avoid the rational roots theorem because 32 has a lot of factors, and that would mean having to try a lot of different numbers. So before I get into the situation where I want to do that, let's try to factor by grouping. So let's just start by trying to do it as is. So here, they both have an x to the 4th in common. So I get x to the 4th, and this is x plus 2. And these both have a, remember, the goal is to try to see, is there any way we can get this to be also x plus 2. It has to be, or the factoring by grouping won't work. And as it turns out, if this is minus 16, right, negative 16 times x is negative 16x, negative 16 times 2 is negative 32. So I get x to the 4th minus 16 times x plus 2. And am I done? Not quite, because this is a difference of squares. So I get x plus 2, because remember, this is the last type of situation, and that is it a quasi-quadratic? Something that doesn't look like a quadratic, but it sure does act like one. So that brings us to the end of this video, folks. But does it? Whoa! I just noticed something. It does not, because this is x plus 2 times x minus 2 times x plus 2 times x squared plus 4. That's a real challenge there. I forgot to break that last one down. All right, so here we go. This is what we've got here. Wow, so this is actually x plus 2 squared times x minus 2 times x squared plus 4. All right, so now we got our final answer. And this brings us to the end of our video. And so I hope that this made sense to you. Please make sure you understand the different cases so that we can have a successful quadratics recap today. Best of luck. Have a wonderful day. And don't forget to love math.